Welcome back to the deep dive. Today, we are going to try to wrap our heads around a number that, it honestly just stops making sense after a while. 1 trillion.
Right, yeah. It is it's a number you hear a lot in AI these days, trillion
Yeah.
parameter models. It's basically the new benchmark.
Exactly. We see the headlines constantly, right? GPT-4, Gemini, Claude, they are all just massive. But I think a lot of us, and you listening might be in this boat too, we just accept that size as a given. We think, oh, it's smarter, so of course it must be bigger. But we rarely stop to ask, how on earth do you physically fit something that big onto a computer chip?
And that is the question. Because it's not just about buying a bigger hard drive or, downloading a larger file. When you get to this kind of scale, you hit what engineers actually call the memory wall.
The memory wall, it sounds very sci-fi, but I gather it's a very real physical barrier.
Oh, it is. It represents the point where your ambitions basically exceed physics. And today we're talking about the sledgehammer that broke that wall down. We're looking at a really landmark paper from Microsoft Research. It's called ZeRO Memory Optimizations Toward Training Trillion Parameter Models.
This is really the how-to guide for the modern AI explosion, isn't it? Like, without this architecture, the generative AI we use today might not even exist.
It's very likely it wouldn't, or at least it would be incredibly slow and exclusively the domain of maybe one or two companies with supercomputers the size of small cities. ZeRO completely changed the math of what's possible. It essentially turned a hardware problem into a software solution.
So our mission today is to figure out exactly how they did it. How do you fit 1 trillion parameters onto hardware that used to just choke on a few billion? And I guess the spoiler alert is right in the name, ZeRO. ZeRO Redundancy Optimizer.
Exactly. It's a story about efficiency. It turns out the way we were training AI for years was just incredibly wasteful. We were hoarding data like digital pack rats, and ZeRO was the intervention.
Before we get to that solution, though, I think we have to understand the problem. I want to start with the why. Why do these models take up so much space in the first place? Because I look at a file size for a model, and it doesn't seem all that scary.
Yeah, let's walk through the math. It's actually really fascinating. Let's take a quote-unquote small model by today's standards. GPT-2, the 1.5 billion parameter version.
1.5 billion parameters. Okay, so if I download that model just to run it on my laptop, the file size is what exactly?
If you store the weights in standard 16-bit precision, which is pretty typical, it's about 3 gigabytes.
3 gigabytes. That's nothing. My phone has more RAM than that. A high-end gaming GPU has 24 or 32 gigabytes easily. So if I have a 32 gigabyte card and the model is only 3 gigabytes, I should be able to train it with plenty of room to spare, right?
You would definitely think so.
Yeah.
But that is the exact trap. There is a massive, massive difference between using a model, what we call inference, and training a model. When you're just using it, you only need those 3 gigabytes of weights.
Yeah.
But when you're training it, you need a ridiculous amount of scratch paper.
Scratch paper. I like that image. So what exactly are we writing on this scratch paper that takes up 10 times more space than the actual book itself?
Primarily, it's the optimizer states. This was the big realization in the paper, actually. The majority of the memory isn't the model itself, it's the bookkeeping required to learn.
So we're talking about algorithms like Adam, right? That's kind of the gold standard for training these things.
Right. Adam is great at learning, but it is an absolute memory hog. To update a single parameter effectively, Adam needs to track two specific things, the momentum and the variance.
Let's unpack that a bit, because those sound like physics terms. What are momentum and variance in the context of teaching an AI?
Sure. So think of the model as a ball rolling down a really complex, misty, hilly landscape, and it's trying to find the absolute lowest point, the perfect answer or lowest error. Momentum is basically the velocity. It says, I'm rolling fast in this direction, so I should probably keep going that way, even if there's a little bump in the road.
Okay, so it keeps it from getting stuck in small potholes. And variance.
Variance tracks how bumpy or unstable the terrain is. If the path is wobbling all over the place, Adam knows to be more careful to take smaller steps. If it's smooth, it can speed up.
So for every single parameter, all 1.5 billion of them, we aren't just storing the value, we are storing its speed and its stability history.
Precisely. And here is where the bit width really bites you. We train with mixed precision. We keep the model weights in 16-bit to save space and speed up the math. But to do those precise updates with Adam, to track that tiny, tiny momentum change, we need a master copy of the weights in 32-bit, plus the momentum in 32-bit, plus the variance in 32-bit.
Whoa. So for every tiny 16-bit weight, we are carrying 3 separate 32-bit chunks of heavy baggage.
Yes, it works out to about 16 bytes of memory for every single parameter.
Yeah.
So do the math on our 1.5 billion parameter model.
1.5 billion times 16 bytes. That is roughly 24 gigabytes.
24 gigabytes. Just for the model states. You haven't even loaded the training data yet. You haven't calculated the gradients. You haven't stored any of the activations.
And just like that, my 32 gigabyte card is completely full. It's bricked.
Exactly. You were out of memory. And that is for a tiny 1.5 billion parameter model. Now imagine trying to do that for 175 billion or a trillion.
Okay.
The memory requirement scales linearly. A trillion parameter model would need roughly 16 terabytes of memory just to turn on.
Which at the time this paper was written simply didn't exist on a single chip. I mean, it barely exists now on a single node. So clearly, they couldn't do it on one chip. They had to use clusters, groups of GPUs working together.
Right. We've been using clusters of GPUs for a long time. But the way we used them was, well, let's call it primitive.
This leads us to the two big schools of thought before ZeRO came along: data parallelism and model parallelism. Let's break those down.
Sure. The industry standard was data parallelism, or DP. That's the easy button. Yeah. Let's say you have 64 GPUs. You take your model and you clone it 64 times. Every single GPU gets a full copy.
Okay, so I have 64 chefs, and they all have the exact same recipe book.
And they all cook a different part of the meal, different chunks of data. Then at the end, they shout their results to each other and update their recipe books all together.
Yeah.
It's fast because they work independently for the most part.
But I see the problem immediately based on our math earlier. If my recipe book, the model, plus all that scratch paper is too big to fit on the counter,
then you can't have 64 chefs. You can't even have one. Data parallelism fails the moment the model is bigger than a single GPU's memory. Okay. It hits a hard wall. You simply cannot load the file.
So then you have to do the hard thing. You have to literally rip the book in half. Model parallelism.
Right. You put half the layers on GPU 1 and half on GPU 2.
Yeah.
Now you have enough memory, but now you have a massive communication nightmare. GPU 2 can't do anything until GPU 1 finishes its layers. They are constantly passing data back and forth.
It sounds like a relay race where everyone is just standing around waiting for the baton.
It is. And every time you pass the baton, you pay a communication penalty. It slows everything down massively. Plus, it is incredibly hard for scientists to code. You have to manually figure out exactly where to cut the model. It requires serious model refactoring.
So we were basically stuck. Data parallelism runs out of memory. Model parallelism saves memory, but is slow and just incredibly difficult to implement.
That was the landscape.
Yeah.
And that is exactly what brings us to ZeRO. The researchers looked at data parallelism and asked a very simple, very provocative question. Why does every single GPU need a full copy of the optimizer states?
That is the redundancy. If I have 1,000 GPUs using data parallelism, I have 1,000 copies of that momentum and variance we talked about.
Exactly. And that is terabytes of wasted space. ZeRO stands for Zero Redundancy Optimizer. They realized that while every GPU needs to use the data, it doesn't need to store it permanently.
This is where the paper gets really clever. They break the solution down into 3 stages. It's almost like levels of a video game, unlocking more and more space at each level.
That's a great way to view it, actually. Let's look at stage 1, optimizer state partitioning. They call it POS.
So instead of everyone holding the full bag of optimizer tricks,
we split the bag. If you have 64 GPUs, each GPU becomes the guardian of 1/64th of the optimizer states. I hold the momentum for this chunk, you hold the momentum for that chunk.
But wait, if I'm GPU 1 and I'm processing data, don't I need updated weights for the whole model to actually do my job?
You do, but you don't need to do the math to update them yourself. At the end of the step, we all just synchronize.
Well,
I tell everyone here are the new weights for my section, and you tell everyone here are the new weights for yours.
so we share the updated answers, but we don't share the scratch paper used to get there.
Perfectly put. Just by doing that, just splitting up that momentum and variance, they reduced memory consumption by 4x. Suddenly, models that were impossible became easy.
4x is huge. That takes our 24 gigabyte requirement down to 6 gigabytes. But they didn't stop there. Stage 2 targets the gradients.
Right. Gradients are the instructions that tell the weights which direction to move. Usually, every GPU calculates gradients for the whole model. ZeRO said, no, let's partition those too. Since I'm only updating my specific chunk of weights, I only need to store the gradients for that specific chunk.
So we are slicing the pie thinner and thinner. What does stage 2 actually get us?
That brings the total memory reduction to 8x. But the real magic, the holy grail of this whole paper, is stage 3, parameter partitioning.
This is the one that melted my brain a little when I read it, because now we are splitting the model weights themselves.
Yes.
But if I am a GPU and I need to run a forward pass, I need to calculate the answer. I need the weights, all of them. If I only have layer 1, how do I calculate layer 10?
This is where high-speed communication really saves the day.
Huh.
Imagine we are sitting at a massive round table. I have the salt, you have the pepper, someone else has the hot sauce. I need to season my food. I don't need to own the pepper shaker permanently, I just need it for 1 second.
So I just asked you for it.
You broadcast a request. You say, I need the weights for layer 10. The GPU holding layer 10 blasts that data to everyone. You grab it, do your calculation, and then this is the absolute key, you immediately delete it.
You delete it.
You throw it away.
Wow.
You treat the model parameters as temporary data. They flow through the GPU, do their job, and vanish to make room for the next layer.
That is incredibly bold. So the model isn't living statically on the chip. It's shimmering through the cluster.
That's a beautiful way to put it. Shimmering through the cluster. Yes. This means the memory usage per GPU is no longer tied to the size of the model. It's tied to the number of GPUs you have. If you have enough GPUs, you can split the model into tiny, tiny fragments.
The memory reduction becomes linear. 64 GPUs, 64x reduction, 1,000 GPUs, 1,000x reduction.
Exactly. With stage 3, a trillion parameter model becomes just a math problem, not a storage problem. They calculated that with 1,024 GPUs, each card only needs to hold about 16 gigabytes of data.
Which fits on a standard card. That's the breakthrough. They turned a hardware impossibility into a software management issue.
It allows the cluster to act like one giant unified GPU memory bank. But of course, nothing in computer science is ever free.
Right. I was waiting for the catch. The no free lunch theorem.
We solved the model memory. But remember when we listed the things taking up space, there was one more bucket. The residuals, the activations.
Right. The intermediate results. If I'm a neural network and I have 100 layers, I have to remember the output of layer 1 to calculate the backpropagation later on.
Exactly. And for a massive model, those activations can actually be larger than the model itself. If you solve the model memory, but ignore the activations, you still crash. ZeRO had to tackle this too. They call it ZeRO-R.
Zero residuals.
They applied a similar partitioning logic, splitting the activation checkpoints across GPUs. But they also did something very practical that I absolutely loved. They built a memory defragmenter.
Defragging, like running the disk cleanup on my old Windows 95 PC. I can literally hear the hard drive crunching right now.
It's the exact same concept. Think about it. During training, you are constantly allocating memory for a tensor, then deleting it, creating a buffer, destroying it. Your GPU memory starts to look like Swiss cheese. You might have 10 gigabytes free overall, but it's all in tiny 1 megabyte holes scattered everywhere.
And if you need to load a 1 gigabyte tensor and you don't have a continuous block of space,
crash. Out of memory error. Even though you technically have the space, ZeRO-R actively manages these memory gaps. It pre-allocates continuous chunks so that you never get that fragmentation.
it's like playing Tetris perfectly every single time.
And in the absolute worst-case scenario, if you really truly run out of GPU memory, ZeRO has one final safety net. It offloads the data to the CPU RAM.
But wait, isn't CPU RAM incredibly slow compared to GPU memory? It's like driving a Ferrari and then hitching it to a mule for the last mile.
Ideally, yes, you want to stay on the GPU. But remember the scale we are working at. These models are so dense, so mathematically complex that the GPU spends a really long time crunching numbers on the data it already has. This is called arithmetic intensity.
So while the GPU is busy doing the heavy math, the system can sneakily move the next batch of data from the CPU in the background.
Exactly. You hide the communication latency behind the computation time, so you get the massive capacity of the CPU RAM without paying a huge penalty in speed. It prevents the system from crashing, which is the most important thing.
So you put it all together, partitioning the optimizer, partitioning the gradients, partitioning the parameters, defragging the memory, offloading to CPU. This isn't just a theory. They actually built this and ran it.
They did. They used it to train Turing NLG. At the time of the paper, that was the heavyweight champion of the world, 17 billion parameters.
17 billion. And remember, before ZeRO, standard data parallelism capped out at 1.4 billion. So this is an order of magnitude leap instantly.
And the performance was shocking. They hit 15 petaflops of throughput. But the stat that really blew my mind was the superlinear speedup.
Yes, I circled that in the paper. Super linear. Usually if I double my computers, I expect to double my speed. Maybe a little less because of overhead. But super linear implies that doubling the computers more than doubled the speed. That sounds like they broke physics. How is that possible?
It does sound impossible, but here's the logic. GPUs are weird beasts. They are most efficient when they're working on huge chunks of data at once, large batch sizes.
Okay, so they like big bites.
They love big bites. But before ZeRO, the memory was so full of model states that we had to feed the GPU tiny bites, small batch sizes. The GPU is starving, basically waiting for data running inefficiently.
I see where this is going. Because ZeRO cleared out the memory clutter?
It opened up massive amounts of space on the card.
Yeah.
That allowed the researchers to increase the batch size drastically. They could finally feed the GPU the big bites it wanted.
So by adding more GPUs, you aren't just adding compute power. You are creating the memory conditions that allow every single GPU to run more efficiently than it did before.
Exactly. It's a compounding effect.
Mm-hmm.
You get the linear speed up from more chips, plus an efficiency boost from better memory management. Hence, super linear.
That is a fascinating insight. It's not just about more power, it's about unlocking the power you already had but just couldn't use.
It really is.
I want to pivot to a word the paper uses a lot, democratization. Because when we talk about supercomputers and petaflops, it feels very elite. But the paper argues ZeRO is actually a tool for the little guy, relatively speaking.
Relatively speaking, yes. Before ZeRO, if you wanted to train a 10 billion or 13 billion parameter model, you needed a team of PhD systems engineers. You had to rewrite your model code to split it across chips manually. It was hard.
It was a huge barrier to entry. You basically had to be Google or Microsoft.
A massive one.
Duh.
ZeRO abstracts all that complexity away. To the data scientist, it looks just like standard data parallelism. You write your code once, and ZeRO handles the splitting, the broadcasting, and the defragging entirely in the background.
So a researcher at a university or a smaller startup who maybe has a modest cluster, they can now punch way above their weight class.
Exactly. They can train models that simply wouldn't fit on their hardware before. It lowered the floor for entry into the large model club. You don't need to refactor your model. You just change a few lines of configuration.
But let's look at the ceiling for a second. The paper is titled, Toward Training Trillion Parameter Models. At the time they hit 17 billion. Did they actually prove a trillion is possible?
Theoretically, yes. They ran the projections. With 1,024 GPUs in ZeRO Stage 3, a trillion parameter model absolutely fits in memory. The math holds up.
But fitting is one thing, training is another.
And there is the rub. ZeRO solved the memory wall. It knocked it down completely. But it revealed the next wall hiding right behind it, the compute wall.
The sheer amount of time it takes to actually do the math.
Right. They estimated that even if you could fit a trillion parameter model on 1,024 GPUs, it would take over a year of continuous running to train it.
A year? That's just not practical. By the time you finish, the architecture is already obsolete.
Exactly. So ZeRO made it possible to store the model, but we still needed much faster chips, next-generation hardware, to make it practical to train within a reasonable time frame, like a few weeks or months.
But here's the real legacy. ZeRO laid the software tracks.
Yes. When the hardware train finally arrived with the H100s and the exaflop supercomputers, the software was already ready and waiting. ZeRO is what made the training of models like GPT-3 and the current generation of giants possible.
So models like GPT-3, GPT-4, they are standing squarely on the shoulders of ZeRO.
Absolutely. The optimizations in this paper are now standard in libraries like PyTorch and DeepSpeed. If you were training a large model today, you're using ZeRO whether you actually know it or not. It's just part of the plumbing now.
It really changes how you look at innovation. We get so obsessed with the hardware specs, how many teraflops, how many transistors. But this was purely an algorithmic innovation. It was just smart code.
It was smart management. It was realizing that we were being incredibly lazy with our resources. By being smarter about how we move data, we unlocked performance that would have cost literally billions of dollars in hardware to match.
It's the ultimate work smarter, not harder.
It really is.
So I want to leave you listening with a thought about that democratization aspect we touched on. We talked about how this helps university researchers, but follow that trend line all the way out. The efficiency of these optimizers keeps getting better. The hardware keeps getting better. The memory wall is being pushed further and further back every day. Today, we are already seeing people fine-tune massive models on consumer gaming cards in their bedrooms. Techniques like QLRA and quantization, which share some spiritual DNA with ZeRO, are making this accessible to pretty much everyone.
We are. We're seeing a massive shift from centralized AI, where only the tech giants can play, to a much more decentralized AI.
So the question is, what happens when the ability to train a state-of-the-art model, or at least a very capable one, isn't limited to a billion-dollar data center? What happens when ZeRO-style logic allows a garage inventor to build something that actually rivals the giants?
That is the ultimate wild card. When the cost of intelligence drops to zero, pun intended, innovation creates a sort of Cambrian explosion. We might see highly specialized models for absolutely everything built by literally everyone. It's the chaotic future, but a incredibly exciting one.
Chaotic, creative, and powered by some very clever memory management. That is all for today's deep dive into ZeRO. The paper is well worth a read if you want to see the math yourself, so definitely check that out.
It's an absolute classic in the field.
Thanks for joining us on this deep dive. Keep optimizing, and we will catch you on the next one.